Hey everyone. So, have you ever tried to move something really heavy with a friend? Like a car that's stuck, or maybe just a super stubborn couch. You're both pulling, but are you really pulling in the smartest way? Well, today we're going to tackle that exact kind of problem head on with a little bit of physics. So picture this. You and your friend are pulling on something, but you're not lined up perfectly. You're pulling at slightly different angles. How can you be sure your combined effort is actually doing the job? Are you working together efficiently, or are you accidentally working against each other, even a little bit? That's the big question we're digging into today.
Okay, let's get specific. Here's our mission. We need to figure out the forces involved in pulling a disabled car. We've got two ropes, and each one is pulling at a unique angle. But here's the catch, and this is super important. The car absolutely has to move in a perfectly straight line down the road. That one single rule changes everything.
All right, let's treat this exactly like what it is, a real-world physics puzzle. And with any good puzzle, the very first step is to lay out all the pieces, separating what we already know from what we're trying to figure out.
So here's our cheat sheet. For the first rope, we know it's pulling with 2.2 kilonewtons of force at a 30-degree angle. We also know the second rope is at a 25-degree angle. And that's it. That's all we've got. From just that little bit of info, we need to find two crucial things. First, how hard is that second rope actually pulling? And second, what's the total combined forward-moving force on the car?
Now hold on. Before we even think about touching a calculator, we've got to visualize this thing. You wouldn't try to navigate a new city without a map, right? Well, in physics, our map is a force diagram.
And here it is. This is our map. It turns out this whole complicated scenario can be boiled down to a simple triangle. Pretty cool, huh? Each side of this triangle represents a different force. The length tells us how strong the force is, and the angle tells us the direction. If we can understand this triangle, we've basically solved the puzzle.
So let's start filling in the details on our map. You see this side right here? That's our first rope. That's the force we already know, the 2.2 kilonewtons pulling at that 30-degree angle relative to where the car's heading.
And these other two sides, well, that's our treasure. TAC here is the tension in the second rope. That's our first unknown. And then there's the base of the triangle, labeled R. That's the big one, the grand prize. That's the total effective pull, what physicists call the resultant force. So we have our map, this force triangle. But to get the answers that are kinda locked inside of it, we're gonna need a special key, a mathematical tool that lets us unlock all the triangle's secrets. But first, before we get to the key, let's just make sure we're totally clear on what this resultant force, or R, really is. Think of it as the net effect. It's the one single force that does the exact same job as all the other forces combined. For us, it's the pure, straight-ahead pull that's actually getting that car moving. And here it is, our secret weapon. It's called the law of sines. Now, it might sound a little fancy, but it's an incredibly powerful rule from trigonometry. All it says is that for any triangle, if you take the length of a side and divide it by the sine of the angle opposite it, you'll get the same number for all three sides. This is the key that's going to connect all the pieces of our puzzle.
So let's translate this law of sines into the language of our problem. We know our 2.2 kilonewton force is opposite the 25-degree angle. Our unknown tension, TAC, is opposite the 30-degree angle. And our resultant force, R, is opposite that big 125-degree angle. And just like that, look at that! We've created a set of equations that connects everything we know to everything we want to find. We have a plan.
All right, enough with the theory. It's time to get our hands dirty and actually run the numbers. Let's walk through this one step at a time and knock out our two unknowns.
First up, our initial target is the tension in that second rope, the force we've been calling TAC.
So to find this, we don't even need the whole three-part equation. We just need to grab two pieces of it. The part with our unknown, TAC, and we'll set it equal to the part where we know all the values. It's just a nice, simple comparison.
Now for a little bit of quick algebra. Nothing scary, I promise. To get TAC all by itself, we just need to multiply both sides by the sine of 30 degrees. That just moves it from the bottom over on the left to the top over on the right. And now we have a nice, clean equation to solve.
And when you punch all of that into a calculator, what do you get? Boom! 2.60 kilonewtons. There it is. We now know exactly how hard that second rope needs to pull. First mystery solved. Okay, one down, one to go. Now for the main event, the answer we've all been waiting for. What is the total effective force R that's actually pulling this car forward? And you know the drill by now, right? The process is exactly the same. We take the ratio with our new unknown, r, and we set it equal to our good old reliable ratio where we know everything. Same logic, just a different target. So again, we do a quick little rearrangement to solve for r, plug in the numbers, and we get our final answer, 4.26 kilonewtons. That is the real deal, effective, straight-line force that's actually moving the car down the road.
Okay, so let's take a breath. After all that mapping and all that math, what do we actually figure out? Let's pull everything together and see what these numbers actually mean in the real world.
So here's the bottom line. The person on the second rope needs to pull with a force of exactly 2.60 kilonewtons. When they do that, the combined effective forward pull on the car is going to be a solid 4.26 kilonewtons. We've just turned a confusing, messy situation into a precise set of instructions.
You know, it's amazing to think that this whole solution worked because of one critical detail from the very beginning. We insisted that the car had to move in a straight line. That single constraint was the linchpin. It's what allowed us to form that perfect, closed triangle and solve what seemed like a really tough problem.
And that brings us to one last thing to chew on. We figured this out for 2 ropes, no problem. But what if a third friend shows up to help? They grab a third rope and start pulling at a completely new angle. How would our forced triangle change then? Or would we need a new shape entirely? Something to think about. Thanks for diving into this with me today.